let's move into Chapter 26. I told you that Chapter 26 is now pretty much, well, except for some of the later sections, it's pretty much just an application of those fundamental rules. So if we are going to look at, for example, a circuit that contains, let's have a resistor, a resistor, a resistor. Okay, so this is R1, R2, and R3. And this is some voltage V, again, plus and 0, but I think you guys have that by now. Let me do that just so you guys can, I'm sure you guys can see it. All right, so that's the circuit we have, and the question is, what, for our purposes of analysis, could we replace all of these resistors with a single resistor just to make our life easier? And that's what we're going to take a look at. Well, how are we going to figure this out? Well, what do we know? We know that the voltage here is V, and we know the voltage here is 0. Okay, so now what else do we know? We know that this is one loop. So it's a kind of a very trivial application of Kirchhoff's junction rule, but Kirchhoff's junction rule says all the current that comes into a junction must leave through that junction. So all the current that goes into this point must leave through that point, and all the current that goes to this point must leave through that point, leave through here, etc., etc. So since there is only one path, there's no adding up that's necessary. We can just say the current that goes through anywhere in the circuit is the same as everywhere. Okay, so we know we have some current I in here. All right. So what else do we know? We know. So now we've done the actually not in order, but we've done a couple of those rules. We have not yet used, however, Ohm's law, V equals IR. So now we're going to use that. Well, we know that there's some current I going through here. So what is the voltage difference between here and here? Well, there's Ohm's law telling us it's I times R1. What about over here? It's I times R2. What about over here? It's I times R3. And we have V here. So what do we now know? We now know that the magnitude of the voltage V, if we go from here to here, we know we have moved in minus V. We're not going to worry about that because all we're worried about is the magnitude. But we know we have a potential difference of V. Happens to be negative, but we, like I said, we're going to ignore that just because we have taken into account. So what do we know? If we go from here to here, we have potential difference of V. If we go from here all the way around here, what must the potential difference be? It has to be exactly the same. But we know all the little pieces of it. We know one of them is IR1, another piece is IR2, another piece is IR3. Okay. But meanwhile, we know Ohm's law again. We know V equals IR. So if we divide this by I, what would V over I be? V over I is going to be equal to R. Well, in this particular case, I'm going to divide this by I, so all these I's go away, and what we end up with is whatever the equivalent resistance is for this whole circuit. And what does that end up being? It just ends up being R1 plus R2 plus R3. R1 plus R2 plus R3. Okay? And I kind of promised you, I denigrated Giancoli a little bit by making a big deal about internal resistance of a battery. And the reason is exactly this. If we could just say that this right here, this R was the R sub I, the internal resistance of this battery, and then the rest of this analysis would be exactly identical, right? So we don't care whether this R1 is outside the battery or inside the battery. It's the exact same analysis. So you can look at the example in the first section there to get an idea of how to accommodate that. but it really, conceptually, there's no difference whether this being outside or inside the battery. Okay, that is enough to start with. That is, oh, and just as a summary, this is how these resistors, because there is only one path for current to flow, we call this a series. One comes immediately after the other, and any charge that goes through here must go through all of them. So any current that's going through here is the same everywhere. So that's what we call a series circuit. So resistors in series, the equivalent resistance is we just add R1, R2, R3, and that gives us the resistance that we would have to replace this whole thing by for this circuit to have the same amount of current going through it. And that's all an equivalent resistance means. Okay, you're done.